Now we have our vector f, we have our vector delta s, and we've projected f onto delta s, and we've obtained this projection, which is projection onto delta s of f, and this is the component of f in the direction of delta s. We still want to find the component of f perpendicular to delta s. So what we can do is we can sketch a line here that's perpendicular to delta s if we want, and we can project f over here and see that the vector that we're trying to get, the vector that we're after, is this component now perpendicular. This is the component perpendicular. I'm not going to write all that out. How do we find that component? If we consider this whole figure here, this is a rectangle. All these angles are right angles. This is a right angle, and this is a right angle. Of course, this is a right angle down here, so that this side is not only parallel to this side, it has the same length, meaning that this vector here that moves right along the original projection line is equal to the component perpendicular. So let's call that perpendicular component. And let's see how that perpendicular component is related to the vectors that we have, namely f and the projection of f onto the direction of delta s. We see very clearly that the projection, and I'm just going to abbreviate this, the projection plus the perpendicular component is equal to f. Put a vector over perpendicular component, an arrow to indicate that this is a vector, and it follows then that the perpendicular component equals f minus the projection. So we could write f perpendicular for the perpendicular component equals f minus the projection. Remember, the projection is just f dot delta s over magnitude of delta s multiplied by delta s over magnitude of delta s. And that gives us our perpendicular component. So we have the parallel component in the direction of delta s, and just by subtracting that from our f vector, we get the perpendicular component.